Yeah, so that brings us to work energy principle. What exactly is work energy principle? Work energy principle simply says that work done is the same as the change that happens in energy. So change in energy is equal to work done. That's what it means. So if I were to write it here, work energy principle will simply mean work energy principle is that work done equals the change in energy. Okay. Now, because we know from law of conservation of energy that energy is not created, it is not destroyed, but it is converted from one form to another. Okay. That is what work is. So you can say that work is equal to how much energy you apply. All right. So this is really useful when we are trying to find out work done and we don't have force, or maybe we don't have, we are doing some work and we want to calculate the energy that is spent, but we don't have enough data to figure that out. I'll give an example. Let's suppose there is a hill over here and the hill is at a height of 20 meters. And we have a ball here. We push the ball down, and the ball has a mass of 2 kgs. All right, so the ball comes down over here, and then we have a sandy situation here. So the ball quickly comes to stop. Like the moment it hits the foot of this hill, it stops. So if they ask us what is the work done, then we will have to calculate that. All right, what is the weight pushing it down? And then we'll calculate that weight and we'll see, okay, it's coming down, the distance and all that. So how much is the work done depends on the change, the force and the displacement. We don't have the force. And if you try to figure that out, it might be a little difficult to do that because it's moving at an angle. So, and the weight is always downwards. So there's an angle involved. So it will be difficult a little bit to figure out how much work is done and what is the force that's causing it. But on the other hand, if you look over here, that it is coming from a height. So whenever there's height, there's potential energy. So over here, it has a potential energy, right? Which is equal to mgh. And over here, we're assuming that the height is 0. And so the potential energy is 0. And we also say that it comes to stop right after it comes here. So what is the work done? You simply calculate what is the change in energy. So energy at the top minus energy at the bottom, and those two will tell us what the change in energy is. So at the top you have mgh, and at the bottom you have 0 as far as potential energy is concerned. And the kinetic energy, we said that it's going to be 0, so it doesn't matter. So work done is simply 2 times 10 times height, which is 20. So we can say that this is 400 joules. So no extra calculation was required. We were able to figure this out right away. Okay, so that is work energy principle. Sometimes the calculations that we need to get the work done can be quite daunting. So we can also use work energy principle if it is easier to find the change in energy. Similarly, when there is a difficulty to find change in energy, we can use the work idea. We can calculate the work and then see that, all right, how much is the energy that is used. Okay, so that's work energy principle. Now the change in energy is also important with regards to power. We define power as rate of doing work. So we get that the change in energy that happens in how much time it happens, that is power. So power is rate of changing energy, how fast or how slow something converts energy from one form to another form. Now obviously it depends on what forms you have, it depends on the machines you have, or it depends on all of that. Okay, so you just have to figure out what form of energy is being converted, and then you can easily calculate the work done in that. All right, so that is power. Now obviously the power that we use in households and all that, we usually pay for the energy. We don't say that, all right, I have an electricity bill, so we usually pay for the energy that we have used. Okay, so usually it is the power multiplied with time that we calculate. That is the energy that we have spent during the whole month or whatever time span you have for which you are being billed. And the units that we have are kilowatt hour. Remember, you might have heard about this कि unit इतने का हो गया या unit उतने का हो गया. What is a unit? Unit is simply 1 kilowatt hour. What does it mean 1 kilowatt hour? It simply means the energy used by something that has a power of 1 kilowatt, that it has the power that it converts 1000 joules one in 1 second, and you run that thing for 1 hour. What is that equal to? That is the energy that is equal to 1 unit. Okay, so आप 1 किलोवाट की चीज लें. 1 किलोवाट usually small irons जो इस्त्री होती है, that is of 1 kilowatt, small irons. Similarly, 1 kilowatt ka, you can say that all right, I have 3 fans running, so that is 1 kilowatt. Or you have a small AC running, so that's a little more than 1 kilowatt. Okay, so it depends on what machine you have and how much energy it converts per second. So watt is something that is telling us how much energy is converted per second. So 1 kilowatt is 1000 joules converted in 1 second. If you have 800 watts, that means 800 joules converted in 1 second. So the units that we have for electricity that we are usually built for are not for seconds, it's for hour, because hour is a more uh, human unit of time. Like we have a higher perception for time in terms of hours compared to seconds. Second is something that we don't really need in a real life. Like we don't really depend on seconds as much. Sure, it does help, and but usually a change in a few seconds doesn't really matter for most of the household things that we do or the things that we do in life.
सर ये पोटेंशियल एनर्जी का फॉर्मूला आपने वो mgh लिखा
Still
हुआ है
can't hear you.
ट्रायंगल से क्या मतलब है उसको बता सकते हैं
The triangle means change. So this triangle is basically delta. Okay, and delta means change.
सर
So
तो फोर्स मल्टीप्लाई बाय डिस्टेंस नहीं लिख सकते
work done is force multiplied by distance. That is the definition of work done. But sometimes it's difficult to find force or the displacement that a body has traveled. So we usually depend on work energy principle. Work energy principle says that the change in energy, whatever energy you change, it is equal to the work done on the body. Okay? So that is what work energy principle is. Now, as I was saying, the power is in kilowatts and the time that we usually take is in hours. Now, how do you convert time in seconds to hours? You know that 1 hour is 3600 seconds. So you can use the ratio method to figure out that if you have 2 hours, how many seconds is that? Or if you have 7260 seconds, how many hours is that? So you know 3600 seconds is 1 hour. So 37260 is going to be X, and you can just cross multiply to figure that out. Okay, so that is how we calculate this. So we convert all the power that we have in our houses, that all the machines that we have run for varying amount of times, and the total power that is spent is divided by 1000 to convert it to kilowatts, and then the total time is converted to hours to calculate the total energy that we have to pay for. Usually the utility companies price it based on how much units you have. So they have certain amount that all right, this unit is for half a dollar or 50 rupees or whatever your currency is. Here's the thing, let's suppose they ask you that here's a question. You have a lift, and that lift is raising mass of 315 kg to a height of 18 meters in 2 minutes. So what is the power that is delivered by the lift? So for that, we'll have to see that, all right, first of all, we know that power is work done over time, but work done is force times displacement. And what is the force over here? The force is of gravity. So it is M into G, and then you have D, you have T, everything just falls in place. You plug in the value. So mass is 315, G is 10, height traveled is 18, and then time taken is 2 minutes, which is 2 times 60 seconds. So you convert this, you divide this, and there you have it. So 315 times 3 divided by 2 is 472 watts. So that means the power that is delivered by the machine in all this time is 472 watts. Okay, now obviously this energy is not what the thing had initially. Okay, so let's suppose they give you a diagram like this. that all right, the machine is like this. So there is this arrow and there's this arrow. So they're like, this is 10% and this is 90%, and this is the energy of the motor or the power of the motor. Now we said that it is useful. So the usually the straight arrow is for useful energy and the bent arrow is for wasted energy. Okay. So we can see over here that 90% of the power of this particular motor is wasted and only 10% is useful. So we'll be like, okay, 10% is 472. Then how much is 100%? We can easily figure that out, that X is going to be 4720 watts. So this particular motor is for 4.72 kilowatts or 4720 watts, but it is only delivering a power of 472 watts. The rest of it, whatever that is, you subtract 4720 and 472, so you get 4248. 400 4248 joules per second is wasted. Another way of saying that is 4248 joules or watt is wasted by the motor. So these diagrams usually help us identifying how much energy is useful and how much is wasted. Now that wasting can be in any form that we don't want. So for example, in this case, we have a lift. So we want the lift to take things up. उसके अलावा हम लिफ्ट से कुछ नहीं चाहते. हम नहीं चाहते कि लिफ्ट शोर में जाए. मतलब if it's a noisy lift or if it's a silent lift, both of those things, as long as it's working, it's good for us. हमें उससे concern नहीं है. Sure, we would prefer having a silent lift compared to a noisy lift. क्यों? क्योंकि लिफ्ट का काम है ऊपर या नीचे लेके जाना. लिफ्ट का काम शोर मचाना नहीं है. अगर हमें शोर मचाना होता तो we would have taken a speaker instead. Something that is designed to do the job that we want it to do. So lift is designed to take stuff up. If it does anything else, then it's not fulfilling its role. And we say that it's not that efficient. We talked about efficiency. Efficiency is how much useful output you have. So if it's in terms of power, that is useful power compared to the total power. If you have it in terms of energy, then it is the useful energy compared to the total energy that it had. So this motor, for example, it was taking 4.72 kilowatts every second. It was taking 4.72 thousand joules, but only 10% was being useful. The rest of it वो उसको जाया कर रही है, वो उसको heat हो सकती है, वो उसको वो मोटर गर्म हो जाती हो, मोटर शोर करती हो. We don't want that. None of that is useful for us. Again, energy तो उतनी है. मोटर ने जितनी एनर्जी ली है उतनी आगे पहुंचाई है, बट हमें delivered for useful purpose बहुत कम है. So we say that this machine is 10% useful because only 10% of the input power is being converted to useful energy.